All right. Tonight I want to talk to you about something I call the Squint test and the fundamental theorem of calculus and how they work together. Now, if you look at the example here, the reason I call this the Squint test is because if you just turned your page on the AP exam and you saw this graphic, right away you could make out that there are shapes here that you're familiar with. Every single time the AP exam gives you a shape you're familiar with, it means you're going to be using geometry somewhere in that problem. That is a foregone conclusion. So when you look at this page and you just kind of squint and you see shapes you're familiar with, keep geometry in the back of your mind. That's something that's going to come up. Now, this problem is often linked with the fundamental theorem of calculus. You can see here that the given statement is that f of x is equal to the integral of g of t dt from t equals -2 to t equals x. That statement is the fundamental theorem, and we want to show how we're going to use this together with the Squint test to answer these types of questions, which are very prevalent on the AP exam. So the first thing I want to do before I jump into this problem is I just want to look at this expression a little bit more. So let's copy this and bring it down here. So a lot of times when you're given this example, you are asked to find f prime of x. Okay, that is very, very, very common. So if they ask you to find f prime of x in this situation, well, not a big deal. You get an equation, we take derivatives of equations. The derivative f of x is easy enough. That's going to be f prime of x. But where we run into trouble is when we're looking at the other side and we've got to take the derivative of this integral. Now, what I tell my students is we can't take derivatives of integrals, not directly anyway. So the way we're going to handle this is we are going to take f of x, and we're going to leave it exactly the way it is on that side of the equation. But now we're going to look at this integral a little different. And we're going to go from t equals -2 to t equals x. And we're integrating g of t dt. So when we integrate this using the fundamental theorem of calculus, little g of t has a parent function, someone that we took the derivative of to get little g. We're just going to give it a name. We're going to call it big G. Okay, and that's basically what the fundamental theorem of calculus uses for standard notation, going to that capital letter. And we're going to plug in both bounds. So we're kind of using big G as a placeholder right now. So when we integrate little g, the antiderivative of little g is big G. And then we're going to have the bounds from x on the top bound and -2 on the bottom bound. So what we've basically done now is we've turned our equation that started off with, this side being side 1 and this side being side 2, and we've now turned it into an equation that really has not just two sides, but now we've got a third side. And the beauty of this is that side 2 and side 3 are interchangeable, so you can pick which one you want to use. So as we go to take the derivative of this equation, the derivative of f of x is f prime of x. I tell my students we can't take the derivative of an integral directly, so instead of using the second side, we're going to go all the way over to the third side, and we're going to take the derivative of that instead. So now I'm taking the derivative of capital G of x. Now, if you remember, g of x was the antiderivative of little g of x, or little g of t, I should say. So what that really means is we've got a situation where big G of x, when we take the derivative, is going to equal little g of x. So using that fact, we're going to get little g of x here. And now we're going to take the derivative of big G of -2. There are two ways to think about this. One, it's a constant. There's no variable there. If there's no variable there, the derivative has to be 0. But just in case you get a little confused, let's go ahead and take the derivative using the chain rule. So if we take the derivative of big G of something, we're going to get little g of something. If we copy the inside for the second step of the chain rule, we're going to get -2. But here's where it all comes together. When we do the chain rule, the third step is to take the derivative of that inside. In this case, that's the derivative of -2. So we're going to have to multiply all of this times 0, and we're going to see that disappear. So what we're going to find out is that f prime of x is equal to g of x. That is an incredibly important result from this, okay? Incredibly important. So remember where we started. We started with f of x was equal to the integral of g of t dt from t equals -2 in this case to t equals x. And by using the fundamental theorem of calculus, we were able to show that anytime we start with this first statement, the second statement we can automatically derive is that the derivative of f of x is equal to g of x. Now, something I keep in mind here. The reason this works the way it does is because our two bounds are what they are. This number down here, it really didn't matter. It was a constant. And as long as that was a constant, that meant that this part right here was going to go to 0. The top part was x. Now that was important because if that had been anything other than x, this problem would have worked a little differently. If this right here is not an x, when we go and take the derivative, we're going to have to use the chain rule the next time. Okay? But because it's an x, that works off like a derivative, a notational one step that we know, the derivative big G is equal to little g. I'll revisit that in just a second. But again, here's our first statement. Our second statement is written down, and now from here we can get a really nice third statement, and that's f double prime of x is going to have to equal g prime of x. These three statements go together in these types of problems almost every single time. All right, so whenever you start with that top one, you know the next two are coming pretty quickly. So this is where the fundamental theory of calculus is in play in this particular problem. So when we back up to the top, and we see that we're starting with this very common expression, we can automatically say, since we know that f of x is equal to the integral of g of t dt from t equals -2 to t equals x, because the bottom bound is a constant, because the top bound is just x, we can automatically go to the idea that f prime of x is equal to g of x, and then we can go to f double prime of x is equal to g prime of x. These three statements, incredibly important to get out there at the very beginning of these types of problems. This is kind of the background information. Once we know this, we can just go and try to answer this question. So we're asked to find f of 4. To me, that means we're going to plug in 4 into the function f. We were given the function f, so the way I like to plug into this is I like to say f of something is equal to the integral from t equals -2 to t equals something of g of t dt. And now we're going to plug in our value of 4. So it's going to be f of 4 there, and that means we're going to plug in the top bound. Basically, what we've got to do here is compute this integral. Now, most students get a little delayed in doing this because they're concerned about trying to figure out what g is. But this is where the squint test comes in. One way we can answer integrals is by using geometry. So if you know the geometry of the shape, that integral can be found using that geometry to our advantage. So we're going to go and we're going to use the geometry. But before we do, I highly recommend that you take a moment to do what I call a sign analysis. We want to find out whether or not this integral is going to have a positive result or a negative result. So when I look at this, the way integration works is we're really integrating a product, which means we're adding up an infinite number of these products. So we've got g of t and we've got dt. Well, most people don't really think about the differential being positive or negative, but the fact is that this dt can take on a negative symbol, a negative sign under certain circumstances. dt comes from the idea of delta t getting closer and closer and closer and closer together and becoming 1 point. So delta t can be negative if t2 and t1 are set up so that t2 is less than t1. In this case, dt is going to work the same way, but what you have to understand is this guy up here is considered t2, and this guy down here is considered t1. So if you think about t2 minus t1 in this case, this would be 4 minus a -2, and that's definitely going to be a positive result. That's going to be positive 6, but all we care about is it's positive. To figure out whether or not your differential is positive or negative, you look at your top bound compared to your bottom bound. If your top bound is greater than the bottom bound, then dt is going to be positive. If the top bound is less than the bottom bound, then dt is going to be negative. So in this case, we know that dt is positive. So now we look at g of t, but remember, we're not looking at the entire function g of t. We're only looking from -2 to 4. So when I look from -2 to 4 in this case, that means I'm going to start here and I'm going to end here. The entire time, this region is above the x-axis, so my g of t is going to be positive as well. That means that we know our result is going to be positive. I always like to do this first because once I figure out the signs, now I can treat every value like it's positive and I don't have to worry about being confused. If I'm going from right to left to right or above the axis or below the axis, all of that is already taken into consideration by doing the sine analysis. So now I'm just going to look at that shape that I just shaded. It's a trapezoid. I'm going to do the average of the bases times the height, and that's going to give me the answer to this question. So when we're talking about a trapezoid, the bases are the parallel sides. So the first side over here has a length of 6. The other base over here has a length of 3. So we're going to get 6 plus 3 for my two bases. And now the height is the distance from one base to the other. We're going from -2 to 4 along the x-axis. So that is going to give us a value of 6. And again, that's from -2 to 4, value of 6. So as far as the AP exam is concerned, this is an acceptable final answer. We could leave it here and be done. I'm going to go ahead and finish this though. So I'm going to do 1/2 of 6 is going to get me 3, and 3 times 9 is 27. So f of 4 in this case is 27. So that's only the first part of this. The second part is to find f prime of 4. Well, f prime of 4, this is where our three equations come in so nicely. We've got f prime of 4 right here being told that f of x is equal, f prime of x is equal to g of x. So let's just plug in. That means when I use that equation, that f prime of something is going to equal g of something. And when we look at this, we're plugging in 4. So f prime of 4 is going to equal g of 4. And g of 4 is something we can deal with easily in this problem. They give us the graph of g. So we're going to go and we're going to take a look at where g of 4 would be. And that's plugging in the value 4. So this location right here is what happens. That will be 4g of 4. And that value is given to us as 3. So we've got the answer to both of these questions by performing the fundamental theorem of calculus along with a little bit of geometry. In part B, we are asked to find all values of x in this interval where f attains a relative minimum value. Now, keep in mind, we still have that the f of x is equal to the integral of g of t dt from t equals -2 to t equals x. And because we have that, we still have f prime of x is equal to g of x. And we also have f double prime of x is equal to g prime of x. Now in this example, they're asking us to find a relative minimum. And anytime we're talking about a relative minimum, in this case, it's the relative minimum of f. That means we want to take the derivative of f and find out where it changes from negative to positive. The derivative of f is already given to us. So what I'm going to do here is I'm going to set up a number line to keep track of where my derivative is positive and negative. So again, that's f prime of x, which is equal to g of x. We're going to put some endpoints on here. We're going to start at -8. We're going to have an ending point on this side of 15. And now we're asking, where does f prime of x equals 0? Well, without this graph, that would be really difficult to tell. But remember, f prime of x is the same as g of x. So we're really asking, where does g of x equal 0? Well, when we go to this graph and we take a look, we're going to find that we have a 0 right here at 5. We have another 0 here at 7. And we have another 0 there at 13. So we've got 3 places, -5. 7, and 13. And these are all zeros for the derivative of f. So now our next question is f ever undefined anywhere? Or is f prime ever undefined? But remember, f prime is the same as g. So everywhere g, in this graph, g is defined. So everywhere f prime is defined. So again, all we've got to do now is go and find out where f prime is positive or negative. So using g as the same as f prime in this case, well, in between -8 and -5, g is negative in that first region because we are talking about the location right here. This is where we're talking about. So in that region, g is negative. Now we're looking in the next region, and that next region is going to be from -5 to 7. So we're going from here to here, from here to here, and then we're going all the way until 7, which takes me to right there. Okay, so everywhere in that region, G is above the axis, so F prime is positive. Now we're going to continue from 7 to 13, and what we see is our function continues to stay above the axis, which means we're going to go up to here and then to here. And everywhere in that region, G continues to be positive. So then finally, we're going to look at the last region, and this is from 13 to 15. So in that region, we're below the axis, so G is negative. So now we know where the derivative is positive and negative. What I like to do here is I like to draw a line graph of my function to kind of keep track of what's going on. So because the derivative is negative, that graph, in this case, F is decreasing. Then the derivative is positive all the way through here, so F is increasing. So now the derivative is negative, so F is decreasing. So this is a rough sketch of what F of X would look like. So now when we go to answer this question, where do we attain a relative minimum? Well, a relative minimum by definition is where the derivative changes from negative to positive. The only place we have where that derivative changes from negative to positive is right here at x equals -5. That is our location of a relative minimum. So we've answered the question. Now we got to justify. Keep in mind, when you justify, you've got to use what you're given. And in this case, we are given the graph of G, which is f prime of x. So all of our justifications has to go back to this guy, the graph of G. So as we try to answer this question, we know our relative minimum is at -5 because of what's happening right here. So what we know is that f prime of x, which is equal to G of x, changes from negative to positive. And that's our answer, okay? Very important that we link the two things. Always, always, always write them both. F prime is equal to G. That way you're making reference to the graph they gave you, which is G, but you're answering the question about F. So always make sure you do that. So as far as this question goes, that is going to get us the credit we're looking for. Part C, very similar. This time we are asked to find an absolute minimum value though, okay? So now we're going to go back a little bit and we're going to take advantage of the fact that we have already made the derivative number line for this guy because he's going to come into play again. So we're going to copy this and bring it back. Okay, so we know that this is the derivative number line. So we're looking for the absolute minimum, and you might be thinking, hey, we just got that. Well, remember, that was the relative minimum. Relative minimums have to happen on the interior. Relative minimums have to have a negative derivative before and a positive derivative after. But when you look at this line graph, you will see there is another person who might lay claim to being the minimum, and that is x equals 15. So in order for us to answer this question, what we want to do is we just want to compare the outputs at -5 and 15. Okay, we just want to compare the outputs. Now, this question also is asking us to justify. Here's a little piece of advice for you on the AP exam. If you're ever asked to justify an absolute maximum or minimum, you're going to make use of something called the candidates test. Basically, we're looking at our number line and we're saying which are the possible values that could lay claim to being the absolute minimum. And we see that -5 is a place where there's a minimum. We see that 15, we're decreasing to that. Here's kind of the weird thing. You always include both endpoints. And I know it doesn't really make a whole lot of sense, but you always include both endpoints. And it's just because when it comes time to justify, if you include both endpoints, you don't have to do anything else for justification than fill out this table. If you leave an endpoint out, now you're into writing sentences. And I'd much rather just let my math speak. The language of love can say it far better than I can. So all we've got to do here is we've got to figure out what f of these three values are. So we're going to go back to our friend f of something equals the integral of g of t dt from t equals -2 to t equals something. And we're going to use this several times. So we're going to start with -8. And I know this is not the answer, but we're going to do it anyway. And we're going to go from -2, which is here, all the way back to -8, which is here. Now, when you do the sign analysis on this, first thing you're going to notice is that dt is always negative. Okay, we're moving backwards. The top bound is greater than the bottom bound. But g of t is going to switch. G of t is going to be positive in this region right here, but it's going to be negative in this region right here, which means I'm actually going to have to think about this as two different regions. I'm going to have to do the part where it's positive, and then I'm going to have to do the part where it's negative. But dt is always negative. So what that means is we're going to get a negative answer for part of this, and we're going to get a positive answer for the other part of this. We're going to add those two answers together, and we're going to get the result of f of -8. What's nice about both of these is they're triangles, 1/2 base times height. And the other thing you may have already noticed is they are congruent. So the base of them both are 3, the height of them both is 6. And what that means is you're actually going to get two areas that are going to cancel out in this case. Okay? Because they are congruent and one's above and one's below, f of -8 is going to end up being 0. So from here, we are going to go and we are going to do the same exact thing, but this time we're going to do it for f of -5. So here we go. T equals -2, t equals -5 of g of t dt, and we're plugging in -5. I'm going to do my sign analysis. The top bound is lower than the bottom, or less than the bottom bound, so dt is negative. From -2 until 5, we are above the axis the entire way. So we're going from -2 until, from -5 until -2, I'm sorry, from -5 until -2. So we're above the axis the entire way, and we are just getting this triangle right here. So g of t is positive, dt is negative. That's going to result in a negative. Using geometry, because of the squint test, we're going to do 1/2 base times height. And the base here is 3, and the height here is 6. So we are going to end up with a value of -9. So we know the output there is -9. Now for the last one we're going to do, this time we're going to have to go and integrate this from f of t dt is going to equal, so f of something is going to equal the integral from t equals -2 to t equals, in this case, we're going all the way to 15 of g of t dt. So when we work this one out, and let me just move this down a little bit here. Let's copy this guy. When we work this one out, we are going from -2 to positive 15. So top bound greater than the bottom bound, that's going to be positive. Sorry, dt is going to be positive. And from -2 all the way to 15, we've actually got to break this into two parts. So the first one is from -2 to 13, where everything is positive. But then we're going to have from 13 to 15, when we're going to have a negative. So doing this from x is between -2 and 13. We know we're going to get a positive result. So it's going to be positive. And now let's look at our shape. Well, -2 to 13 means we're starting here. And we got a couple shapes I'm going to use here. So the first shape I'm going to do is going to be this yellow shape right here, which is a trapezoid. Then the next shape I'm going to do is going to be from 4 until 10. And this one is actually going to be a rectangle with a semicircle chopped out of it. So we're going to have to find that area. And then the last one I'm going to do is going to be from all the way to 13, which is going to be this triangle. And then after that, I'm going to have to go from 13 to 15. Okay, I'm going to go from 13 to 15. But I'm looking ahead, and what I'm seeing is going to make our life a little easier here, because from 13 to 15, these two triangles are going to cancel out, because one's going to be, I take that back, part of the region is going to cancel out. So we're going to go through and we're going to work this out. Okay, so here we go. From -2 to 13, the first shape we've got is a trapezoid. So that's the average of the bases times the height. That's the first shape we've got. The next shape we've got, and again, these are all positive based on the sign analysis, is a rectangle, base times height, minus a semicircle, 1/2 pi r squared. And then the next shape we've got is a triangle, which is going to be 1/2 base times height. We've already seen this trapezoid. We're going to go through it again. I've got a base of 6. I've got another base here of 3. So 6 and 3. And then I've got a height of 6. So there's the area of the yellow piece. Now we're going to do the rectangle next. And this rectangle has a base of 6. And it has a height of 3. And now we're going to look at this semicircle. The semicircle is going to have a radius that goes from here to here, and that's from 7 to 10, so that radius is 3. And then last but not least on this one, we've got a triangle that has a base of 3 and a height of 3. So that is the answer for those shapes. Now we've got to continue and go from 13 to 15. Remember, that's where this sign analysis came in, so we're going to have a negative in this case, and it's going to be a triangle. And this is going to be a base of 2 by a height of 2. So we are going to have to compute this answer. This is going to be, if we do this out, this is going to be 3 times 9, which is going to be 27. 27 plus, this is going to be 18 minus 9 pi over 2. This is going to be 9/2. And then down here, we're going to have a minus 4/2. So if we go a little further with this, 27 and 18, 37, 45, 45. This is going to be minus 5/2. This is going to be 9 pi over 2. So 90/2 minus 5/2 is going to give us 85/2 minus 9 pi over 2. So coming back up here, 85/2 minus 9 pi over 2. We are looking for the absolute minimum. So the only question is, since 0 is greater than -9, we know that's out. Is 85/2 minus 9 pi over 2 greater than -9, or is it less than -9? Well, we're going to do a kind of an estimate on this. We know that 85 minus over 2, let's just kind of say that pi is, we know it's less than 4, so we know this is really going to be 85/2 minus something that's less than 36/2. And that would give us 49/2. That is positive. And we know that's going to be greater than -9. So when we use the pi, it's going to be a smaller answer, but it's not going to even go negative. So we know that the absolute minimum value is -9. Okay, so the absolute min is -9. Now, again, the beauty of this, if we do the candidates test, then this right here is all the justification we need. That will do the trick for us. One last question on this one. So, in this one, the key word they're asking us about is point of inflection. And that is where the second derivative exists and changes signs. So we need to know about f double prime of x. Now, if you'll remember, we've been saying throughout this entire process that f prime of x was equal to g of x, and f double prime of x was equal to g prime of x. So we need to make a number line for f double prime, but that's equal to g prime. So the key here is understanding that for this problem, g prime of x, since derivative means slope, that's the slope of g of x. But since g of x is our graph, this is the slope of the graph. So we want to talk about the slope of this graph right here. So making our number line, we're going to put some endpoints in of -8 and 15. So where is the slope equal to 0? Well, in this graph, there isn't a single place where the slope is equal to 0. I take that back. There is one place where the slope is equal to 0. The slope is equal to 0 right here where the semicircle flattens out. So we've got a 0 slope at 7 because that is a place where the tangent line is horizontal. So the slope of g is 0 at 7. There are, however, 3 places where the slope of g is undefined. In each of these locations, right here, and right here, we say that the slope of g is undefined. And that's because it forms something we call a cusp or a corner. And the idea of a cusp or a corner is that the slope coming from one side does not match up to the slope coming from the other side. And you can see that in all of these cases, that the slopes coming from one direction do not match the slopes coming from the other direction. That leads to undefined slopes in each of these cases. So we've got that the slope is undefined at -2. We've got the slope is undefined at 4. And we've got the slope is undefined at 10. So now all we have to do is figure out where is the second derivative of f, which is the derivative of g, which more importantly for this is the slope of our graph. We know where the slope of the graph is 0. That was at 7. We know where the slope of the graph was undefined. That's at -2, 4, and 10. Now in that first region, is the slope of our graph from here to here positive or negative? And it's pretty clear since our function is increasing that the slope there is positive. Now, if we take a look at the next region and we ask, is the slope of our graph positive or negative in this region? We can see that our function is decreasing, so the slope of g is negative. In the next region, we're talking about the slope from here to here, from 4 to 7. And again, in that region, the graph is decreasing, so g is decreasing, which means the slope of g is negative. In our next region, we're going from here to here, and in that case, the slope of g is positive. And in the last region, we're going from here to the end, and we can see that the slope of g is negative. So in this question, they're asking us, where are the inflection points? We have inflection points any place where f double prime changes signs. So we're going to have an inflection point at -2. We're going to have an inflection point at 7. And we're going to have an inflection point at 10. So x equals -2, x equals 7, x equals 10 are the x values where there are inflection points. This question did not ask us to justify, but if it had, we got to use our graph to do it. The justification would be that f prime, which equals g, changes from increasing to decreasing or vice versa at each of these points. Because where your derivative changes from increasing, if f of x is increasing, another way of saying that is the derivative of f prime is positive. And if f of prime of x is decreasing, another way of saying that is the second derivative of f is negative. So again, just to make sure I said that clearly before, if we know f prime is increasing, it means f double prime is positive. If we know f prime is decreasing, it means f double prime is negative. So we're really saying that the concavity is changing in each of these places. So that is what you need to know about the fundamental theorem and the squint test. If you look at a problem and you see geometry, think about the squint test and then make sure you do a sign analysis to figure out if that integral is positive or negative. Hopefully that was helpful for you.